Welcome to The Explainer. Today, we're exploring a completely fascinating intersection of disciplines: game theory, mathematics, and the elite sports doping crisis. We're going to look at some really compelling research by Katie K. Haugen that asks a pretty bold question. Can we literally engineer a mathematical solution to stop athletes from cheating? I am incredibly excited to guide you through this. We're going to break down these complex scientific models step by step. My main goal here is to make the math totally understandable and, frankly, just a lot of fun to think about.
Okay, let's dive right into this. The central puzzle we're unraveling today is whether academic modeling could theoretically just eliminate doping in sports. Because, usually we think of anti-doping as this endless cat-and-mouse game of biological testing. We're talking urine samples, blood passports, the whole shebang. But what if the actual solution lies in the strategic choices athletes make before the competition even begins? What if we could actually change the rules of the game itself so that cheating is literally no longer the logical choice?
So here is our roadmap for today. We'll start with the doping prisoner's dilemma, introduce the announcement strategy, factor in risk and stigma, see exactly how that changes the game's outcome, look at the ultimate anti-doping sequence, and finally ask, can we trust it?
Let's kick things off with Section 1, the doping prisoner's dilemma.
Now, to make sense of the math we're about to see, we really need to understand one absolutely crucial concept, and that's the Nash equilibrium. Think of a Nash equilibrium as the final locked-in state of a game. It's this predictable outcome where, given what everyone else is doing, nobody wants to change their strategy. Everyone kind of looks around, shrugs, and says, well, given my opponent's choices, this is the best I can do. It's basically a state of strategic gridlock.
So the really important point is understanding what goes into an athlete's head. In this economics of doping model, we've got three core variables. A represents the winning prize. That's the gold medal, the sponsorship money, the ultimate glory. Then we have R, which is the risk of revelation, meaning the literal probability of failing a drug test. And finally, C is the revelation cost. This is the heavy stuff, the bans, the lost income, and the massive cultural stigma of being publicly labeled a cheater. When an athlete makes the call to dope or not, they're subconsciously weighing that incredible prize, A, against the combined threat of getting caught and the resulting penalty. Mathematically, that threat is R times C.
And when we map this out mathematically, you see that both players predictably aim for their best possible replies. Because the prize is massive and the risk is relatively low, the math overwhelmingly pushes both players toward the exact same corner. It creates a Nash equilibrium of dopey-dopey. In this classic model, it is mathematically totally rational for everyone to cheat. It's a tragedy, but it's the logical outcome.
Moving right along to Section 2, the announcement strategy.
Now, imagine escalating the suspense of a massive sporting event. What if, instead of making these choices in secret, athletes use social media or huge press conferences to publicly declare their strategies before the competition even starts? You'd probably think that the sheer public pressure and the spotlight would totally force athletes to change their approach, right?
Well, game theory lets us map out that exact what-if scenario. When we build out this perfect information tree where it's a sequential game and one player announces first, then the next, something really surprising happens. Even mapped out step by step, the mathematical outcome stubbornly ends up exactly where we started. We're still stuck at that dope-dope equilibrium. As long as the players are symmetric, meaning they value the prize and fear the risks equally, the actual sequence of who announces first gives absolutely no extra advantage.
All right, let's get into Section 3. Factoring risk and stigma.
The reality is, athletes are obviously not perfectly symmetric clones. They face vastly different cultural realities depending on where they're from. For example, the source material points to the 2014 Sochi Olympics, where the Russian state allegedly swapped urine samples. For those athletes, the risk of getting caught, that R variable, was practically zero. But contrast that with the 2001 Finnish skiing scandal in Lahti. Over in Finland, the cultural shame, the C variable, was absolutely catastrophic. It practically devastated the nation's entire sporting culture for over a decade. So athletes from different places face totally different risks and massive cultural stigmas. To make the math actually reflect reality, the model needs an update. The risk and cost variables can't be universal anymore. They have to become player-specific. Player 1 has their own risk and cost, R1 and C1. Player 2 has R2 and C2. We are essentially breaking the symmetry of the original game to ask a much better question. What happens when a competitor from a low-risk environment faces off against a competitor from an incredibly high-stigma environment? And when we do that, you see this really subtle shift in the payoff equations. By sprinkling in these specific variables, R1, C1, and R2, C2, the underlying math of the entire game begins to warp. The foundational assumption that everyone values the risk and reward identically is just completely gone. Which brings us to Section 4, changing the game's outcome. Let's set the stage for our new equation. I want you to imagine two athletes. Player 1 is from a pretty standard environment, but Player 2 is from an environment with intense cultural stigma against cheating. For Player 2, the shame of getting caught is so extraordinarily high, and maybe their share of the prize money is even heavily taxed, that the cost of doping fundamentally outweighs the benefit. They are genuinely, truly terrified of the consequences. Because Player 2's specific variables drastically increase their cost of getting caught, the Nash equilibrium literally shifts. We are no longer stuck at dope-dope. The new predictable outcome is dope-no dope, meaning Player 1 dopes, but Player 2 does not. Simply by having one athlete from a high-stigma culture in the mix, the math predicts a 50% reduction in cheating straight away. But let's test our announcement strategy again with this new setup. If we put this asymmetric matchup into a sequential tree where the low-stigma Player 1 announces their choice first, what happens? Well, the outcome stubbornly persists right at dope-no dope. Player 1 announces they'll dope, and Player 2, completely fearing the stigma, decides not to. So it's an improvement, for sure, but it's not a total solution.
Now for the really exciting part. Section 5, the ultimate anti-doping sequence.
Let's see how this all builds together. We know that in a symmetric game, the sequence of who announces first doesn't actually matter. But our players aren't symmetric anymore. One is terrified of the stigma, and the other isn't. So, what if we actively manipulate the order of the game? What if we force the highly stigmatized player, Player 2, to announce their strategy first? And this brilliantly illustrates the absolute power of game theory. In this final sequence, Player 2 goes first and announces no doping. Because of how the math shakes out, Player 1 is now forced into a strategic corner where their only rational reply is also no doping. By flipping the sequence and letting the culturally restricted player lead, we reach a unique no doping equilibrium. In theory, all doping completely disappears. It's mathematically solved. Which leads us to our final part. Section 6. Can we trust it? The huge, obvious, practical question staring us right in the face is, if the math is this airtight and clear, why haven't sports organizations simply implemented this sequential announcement strategy yet? Why isn't this the standard at every Olympic event? Well, because implementing game theory in real life is incredibly messy and complex. The source research highlights some major practical complications. First off, credibility. In a game with such high stakes, why should anyone believe the first player's actually telling the truth about not doping? Second, proving a negative is notoriously hard. How do you genuinely verify a no-doping intention before the race even happens? And third, copycat tactics. What stops the second player from just jumping the gun and screaming, "I'm not doping either," before the first player even finishes their announcement, totally ruining the sequence? It introduces a massive problem of asymmetric information and broken trust. Which leaves us with a really profound final thought. The math proves that if we can leverage varying cultural stigmas and manipulate the order of declarations, we could theoretically just wipe out doping. But implementing it requires navigating this absolute minefield of deception, verifying unprovable intentions, and literally weaponizing cultural shame. So the question isn't just whether math can solve doping. The real question is, if stopping doping relies on manipulating trust and exploiting cultural fears, are we as a sporting society truly willing to play that game? Thank you so much for joining me on this explainer. I really hope this helped make the fascinating economics of doping just a little bit more understandable for you. Keep learning.